Welcome to the real start of calculus. And that's like me being kind of snarky, limits our calculus. Like you've been doing calculus this whole time, but we get more fun calculus today. And for the first time, we're going to start talking about ideas where like applied math is really and truly applied. Remember, Newton and Leibniz developed this. Like Newton was doing physics and he said, gosh, physics sure is hard. I can't make sense of what's going on with algebra that exists today. Oh, but there's this whole other type of math that also exists that we're going to use and develop, and it's fantastic. Chapter 2 is the first of the 3 chapters covering a singular idea. Chapter 2 is the start of our discussion on the derivative. Okay, the derivative is a huge focus. Now, I'm not going to redraw the picture from our bell ringers, but we're just going to try to summarize that statement pretty quickly. Given, and we'll just kind of preface this even before we start talking about stuff. I lied. We'll go 2.1. We're going to talk about rates of change. Rates of change. And the derivative. And I know it's kind of redundant, but we will get a shorthand for derivative in like 2 minutes. Cool. So right off the bat, we're going to preface. And if we want that little picture that we've drawn multiple times with f of x plus h, we can sketch that picture. We should probably have the picture. I'm going to sketch a really lazy picture real quick. And it's like the exact same picture from the bell ringer. X and x plus h. And I'm not going to label the y points though. Okay. We know that if we want to find the secant line, we can find that slope no problem. Now, what we want to do is we want to go from a secant line, which is okay, but we want to know at a single point in time, how fast is something changing? So whether it's an object falling through the air and it's accelerating, I want to know, well, how fast is the velocity changing right here, right now? This is a calculus question. Immediately you can see why Newton would care about developing math to deal with this, because all the algebra stuff that we did in physics last year, while it works, it is so clunky compared to the real math of calculus that's used for this. We're going to do a bunch of physics problems in here. It is not going to be physics class, but all the things with velocity, displacement, distance traveled, all that we're going to look at through a different lens and see, man, if only we had calculus-based physics, things would have been much nicer. Okay, so for this, I'm not going to write that whole problem, but remember, we're going to say the slope m, and I'm going to switch to black because I don't like the way that contrasts. The slope of the secant line, m secant x, or m of the secant, is f of x plus h minus f of x all over h. Now, I don't have a good way to suggest you animate your pages because I can't even do an animation up here. So I'm going to draw and erase and draw and erase and draw and erase. You guys should only draw maximum 2 things. If I pick this, what we have here, this is my secant line that we just drew, right? That is the secant. So we'll say it's that guy. That's my secant line. If I let h get smaller, and there's a few ways we can think about this. I can either say as h approaches what value? If it gets smaller and smaller. So like this value, it could also be an x plus h, but it's way smaller. How small can it get? Arbitrarily. Love the word, Sean. Which means as h, and I'm going to write this, and I want somebody to read this. What did I just write? Love it. Again, approaches 0. Our secant line, our secant, it changes to something. And I'm going to do this one in blue just so we can differentiate. I'm going to zoom way in. That's as far as I can zoom. And to check it out, I can see I missed the point, but not really. Okay, check it out. This is pretty close. Would you guys agree? Can I get closer? Now, because points are infinitely small, they don't have any size, I could get eventually, like that's pretty close as well. But if I get as close as I want, it's going to look like a single point. Like I can tell there's 2 points here and it's kind of hard, but do you guys agree? I'm going to zoom out and I just want to make sure we can see this. I just let that distance h not get to 0, but it got pretty close just now. Can you really tell I have 2 points anymore? Not really, but are there 2 points? And if there's 2 points, can we find the slope? We could draw the line. As h approaches 0, our secant changes to this thing instead. And it's no longer a secant line when we view it. It touches not twice, like it really does touch twice, but we got to do some weird stuff here. We're just going to say it touches twice, but it doesn't, right? Because they get to be the same size. It only touches one time in reality, which means it's no longer a secant, but it changes to a what? A tangent line. Okay. Now, this is the first time that we can, and I'm sure I've mentioned it before, but I just want to recognize, if this is somebody's velocity, can you guys, the red one, can you guys tell that as time goes, they're going faster and faster? So if I wanted to know how fast does their velocity change, that's called acceleration. If you don't recall, that's okay. But how fast velocity changes is acceleration. If I said, what's the slope at this point? It's a weird question, because when we talk about slope, you need 2 points. But when we use this idea, could we conceivably find the slope at a single point then? That's what we've just done. We found the slope of a tangent line. This is the driving force behind everything. This idea, this is the idea of the derivative. So we're going to jump right here. Okay, in calculus, the slope, so we'll do a big comment here. The slope of this tangent line is, and I'm going to get kind of wordy for a second, but I promise it's going to get much nicer right afterward. The slope of this tangent line is the value of the derivative of, what was our function called initially? That red function that we graphed? F, good. And I'll even color code it so it stands out a little easier. At the point x that we've chosen. At the x we've chosen. Okay. As we look at this, this is gross, and the wording is gross, but the value of the derivative is the slope that we're after. So if we estimated, I know we don't have numbers, but if I told you this was a slope of 1/2, it looks kind of like it could be. I would say the derivative at this x value was 1/2, because I'm just telling you the slope of the line there. Now, when we write this, it's so much nicer. We are going to write our last little expression. When we read this, if I'm talking about the slope of my function f, we're not going to call it f, and we're not going to write the slope of my function f. We're going to use very specific notation, and there's a few of them that we'll use throughout the year, but here it is. F, this is an apostrophe, and I hate the way that one looks. I usually just do this. Okay. This is what the math that we want to, okay, weird wording. This sentence is ugly. This is a math for this sentence. Okay, this thing is not f dash c. This is f prime of c. Okay, now we'll clean up what the c and stuff is, but when we want to talk about the slope at a given point, it is simply the limit of the secant line, and that's kind of ugly, but here we go. This is the same thing as the slope m of the tangent line, which we did something to the secant line just now, right? If I let that, is there a mathy way that we say, hey, let something get arbitrarily small or close to something else? Infinitely close, right? And it's a limit that we've been doing with that. So here we go. We'll say the derivative at c, or f prime of c, is the slope of the tangent line, and it is exactly the limit as, we'll see a couple different definitions. The first one, we could call it as x approaches c. And I'll add a couple things to this picture so we can make sense of it. But it is simply going to, and we're going to do that here. Instead of saying x and x plus h, could I have said that this is x and this is c? Like just to make it look a little nicer. Does that say the same thing now? instead of f of x plus h, it would have been f of c minus f of x. Everybody cool with that? Okay, this is just nicer to write. It is exactly the limit as x approaches c of f of x minus f of c all over x minus c. This is it. Now, whether we use the x plus h notation or this notation, it really doesn't matter. They say the same thing, they do the same thing. Each one serves its purpose in a particular situation for how we want to be able to make sense of something. But all that we've said is to find f prime of c, you just take the limit of this slope. Any big questions yet? Okay, so here's what we're going to do. We're going to make sense of this, and we're going to use this idea of the derivative to help us write some linear equations. So we'll have a little subsection here, and I'm trying to stay consistent. I'm going to make it a tilde. Tangent line equation. Now, a little bit of review is naturally going to be embedded within here. If I give you a point and a slope, can you find a line? I'm going to write it on this board. How do I find, if I give you some point and a slope, how do you find the equation of that line? Point slope. Oh, point slope. That works. What's point slope? I'm going to give you 30 seconds to chat with your neighbors. Somebody's going to remember it. 30 seconds. What's point slope is a question at hand. Turn and talk. I'm going to call in one random person. We are going to do the following. If I have a function, doesn't even matter what it is, but here's all we're going to say. Given that the slope of the tangent line exists, and the only time that the slope couldn't exist, remember, is when it's straight up and down. If it's straight up and down, we wouldn't say it exists. If the slope, and there's others, but we'll deal with it. If this exists and we pass through some ordered pair, we'll say, I don't know, like c and f of c, then the tangent line is written, and I'm going to make you guys help me with this. We're going to write the equation of this line. Did I give you a point that we're passing through? I think so, right? Like, we pass through this ordered pair. Here's the harder question. If the slope of the tangent line exists, I didn't tell you what it was, but do we have a slope? And look in your notes for me real quick. What did we say we can call the slope of my graph at point C? Right above this, in your notes, we said something about the slope at C. A new fancy notation. F prime of C is literally our slope, right? That's what we just hopefully agreed on. F prime of C is your slope at C. Okay, that means we have a point, we have a slope. Can we solve this, do you think? Let's try it. We're going to use point slope. It'd be y minus, what's the y value we're plugging in? F of C is equal to, and we could say m, but we're using calculus, the slope at C can be written in new fancy notation. F prime of C. That's like my m value. Times x minus C. And I want you to notice something. I'm not going to expand any further beyond this, but if I were to solve for f prime, I get y minus f of c, which is just a y minus y, that's a delta y, and I would divide it by x minus c, which is exactly what we wrote a second ago. This is just to reemphasize that, hey, as long as we recognize that this is slope, and I'm going to make that super stand out. If you don't need this, don't write it, but this is the slope at x equals c. Then we now have a new looking way to write our line, and nothing crazy has to happen. Okay, have I lost anybody here yet? All right, next to this, I'm going to make another statement. We're going to do way less writing. We have the tangent line equation right in here. We talked about this last year, but we'll see how much you guys remember. Do you ever remember talking in physics about a normal line? or a normal force? The language probably sounds familiar, whether or not, ooh, hit it.
Like the opposite of like what I remember from physics, like the opposite of gravity.
So right now, you guys are all being pulled toward the center of the earth via gravity, right? Why aren't you falling right now to the center of the earth? Your chair is pushing exactly opposite. That's a normal force. When we look at this, that idea shows up here right away. This one's going to be much shorter. We're going to say that the normal line, we're not going to go through all the same stuff, but this is simply going to be the line. If it's exactly opposite, like to your surface, would you agree it's perpendicular then? Like if this marker is sitting here, or I guess my laptop is, it's pushing perpendicular to the surface here. Okay, the perpendicular line, or perpendicular, line to the tangent. Now, if we wanted to do the same thing, if I still wanted to pass through CF of C, but I wanted the normal line instead, help me write that. All the same stuff, but my slope has changed. If I have y minus f of c, how do you find a perpendicular slope, TikTok? Opposite reciprocal. What's the opposite reciprocal of this? 1 over f prime of c is a reciprocal. What about the opposite part? Negative 1 over f prime of c times x minus c. Now, all I've done is opposite reciprocal. That's the TikTok whoa reference every time, which doesn't resonate as well with people younger than you, so you happen to be just the right time in history for that to make sense, because when I use that in other classes, you look at me like I'm an idiot. That's okay. All right, cool. Anything you think we should say is important about f prime here? What can't f prime be equal to? Good. Okay, we now have an equation for a tangent line, and we have the equation of a normal line, which is just perpendicular to it. So here we go. You guys ready to do some more limits for a couple days? Cool, good. Example. I want us to find the equation of, and I'm going to shorthand, tan and normal line. We're going to do the first part together, and then we'll kind of dig in. So let's get crazy with it. On our first example, we are going to be considering our function f of x that is just x cubed. And we're going to find the equation of the tangent line at a c value equal to 1. Now, graphically, doesn't really matter right now if you can tell me exactly what this graph looks like. I'll sketch it up on the board here in a minute, but I don't really care what the graph looks like. If I'm trying to find this equation, I only need two things. I need the slope, and I need a point. So let's get the point first. At c equals 1, that's an x value that I'm picking. X equals 1, or c equals 1. We're just using c to indicate a specific number. Could you tell me the y value for our function? And specifically, I'm just going to reword that through, 1. Well, let's try. F of 1 equals 1. Okay, you're right, Sean. That is, I'm going to put, nope, not going to use that. This is an ordered pair, which I'm just going to say this implies it's the ordered pair 1, 1. You were right, Sean. I can write a point like this. I can write a point like this. They're the same, just different notation. Cool. So we have the point that we run through. What else do I need if I want to write the equation of the line? Oh, no. Or, oh, yeah. I don't know. One of those ways. How do you find the slope of a tangent line? So this, I think, is the last time I ever want to write m, because we're not going to write m anymore for now. We're going to write what? Good. So m, in this case, is equal to f prime of what x value are we plugging in for? We need f prime of 1 is the goal out of this. That's the slope that we need. The question becomes, how on earth do we find this? The great news is we have a lovely, nice way to do it. I'm trying to approach, what C did we pick just now? Okay, so let's just plug into this real quick. This is the same thing as equaling the limit as x approached, what was it again? 1 of, and we get this lovely thing here, and we're going to do it really general, and you will start to save time. I promise, once we do the limits, there's shortcuts coming galore. So it's f of x minus f of, if we use the definition that we wrote above, what should go here? 1 all over x minus 1. Is anybody not quite clear where I got these values from? I wish I could show them both, and I'm actually going to copy it. I'm doing this, where it's f of 1 is what we're finding. So it's just like I put a 1 here and a 1 here. If it wasn't clear, that's all that's just happened. All right, so let's keep kicking. Let's just substitute it in what we know. This is the limit as x approaches 1. What is f of x? X cubed, good. Minus, what was f of 1? 1 all over x minus 1. Love what Fern is doing because he saw something, but if you don't have a calculator because they didn't give you one or yours is malfunctioning, I do want to make sure that we have this. This is special. It's a difference of cubes. If you remember the formula, awesome. If you don't remember the formula, awesome. You have a cheat sheet that we can use. Now, instead of making you go through the process of taking out your cheat sheet and stuff, I'm going to help you, and I want to verify that we get the same thing. Before I do any big fancy work, what's the first thing I should try with a limit? Direct sub, 0 over 0, bummer. Okay, now it's time for fancy work. Does anybody without a calculator remember how to factor this? You're really, really close. Okay, looking at this, the difference of cubes works really nicely. Do you know the cube root of both of these? Mickey, what's the cube root of x cubed? Do you agree it's x? Okay, so here's my first factor, the cube root minus the cube root. And you'll see where you were close, Abigail, on this. Yep, take this term, let's square it. It's x squared. Plus, I'm going to multiply these, I think it's just x. And then I'll do this term plus this guy squared now. It's still 1. Fern, when you and everybody, because I saw people take their calculators out, did you guys find how to factor on your calculator just now? F2, factor, type it in. Okay, all of this is over x minus 1. Anything convenient happen? They're gone. First question I have, if we were talking about continuity, is that a removable or non-removable? We literally just removed it. Okay, yes, it is a removable. So I've rewritten this, and it's going to be redundant, but I want to make my work super clear. This is our new limit. And normally we don't rewrite this one, we just plug it in. But what should I try again now that I have a different looking form? Direct sub. What is 1 squared? Plus 1? Is 2 plus 1? 3. What did we just say was equal to 3 at the end of this? The slope, louder. I liked yours. F prime of 1. Now the slope is the same thing, but I really like that. F prime of 1. And notice, I had it written, I let it ride, and we'll write it again. This is our what of our line? It is f prime of 1, and specifically it's the slope, says Bea. Okay, do we have a point? Do we have a slope? Well, I think we can write the formula. It's y minus 1, okay, equals, what was m, or f prime? 3 times x minus 1. Check it out. This is probably going to annoy you. Maybe it won't. Did I tell you to find the equation of the line in slope-intercept form? We literally just said find the equation of the line, right? Do I have an equal sign here? that an equation? If I don't specify, do we really need to go to the y equals 4? Would you, like, do you want to? Okay, I'm okay if you do, but remember that when we don't have to simplify stuff, if you do go further and you get it wrong, you lose it. So if we simplified, and I'll just write this the alternative, 3x minus 3 plus 1, so 3x minus 2. Cool. We have just done our very first derivative. Is this limit any harder than anything that we've done so far? I don't think so. JJ.
I have a question. How did you get x squared plus x plus 1?
So how I got it is because I know the rule for factoring. Did you get one of the factoring sheets? If you do or don't, doesn't matter. You're going to get another one here.
If you FOILed it,
What I did was I recognized that we had a difference of 2 cubes, and here's the shortcut for it. We could do some big fancy factoring stuff to get that equation. Come see me if you want to do the big fancy factoring to get that equation, okay? Cool.
I get it.
I want you guys to do part 2 of this, because that's only the tangent line, right? Find me the equation of the normal line. Talk it out with your neighbors. I'm going to give you a head start, and then I'll work it. But I want you guys to start. Find the equation of the normal line here. This is all my tangent stuff. I don't have to do the limit again. I'm just going to jump in right here. The slope of the normal is just the opposite reciprocal, 1 over f prime of 1, which negative 1 over f prime of 1, I'm sorry. I think it's just negative 1/3, right? Well, I have a slope. Do I still pass through the same point? Yeah, super easy. Y minus 1 is equal to not 3 anymore, negative 1/3. X minus 1, and we're done. Here's our normal line. Okay, we have found. Do you want to see graphically what we've just really done?
So you don't have to solve it.
Well, there's nothing else to solve. Without even going hardcore with it, if it's pink, it's just for think. Cool. So here's x cubed, roughly. Looks about like this. And what we've just found is that when x is 1, so maybe here, here's our tangent line. And we just found the slope of this was what? 3. And then alternatively, we've also found this line, whose slope is negative 1/3. This is everything that we've done just now. One thing that I probably should have commented on earlier, when we're talking tangents, if you remember from geometry, they touch one time. There's a weird issue that happens. This one right here that I drew as tangent, is it going to touch it again? Did I break the rule of a tangent line? We only care about in that neighborhood. In that region, does it only touch once? Because there's a lot of stuff that it might do wavy things and pass back through. In one very specific region is all we're looking. Cool. All right. Does this seem super challenging? Okay. The equation of a line part is, like, it will show up, I guarantee it, but I think you guys have seen enough algebra that that's not really where we should focus. I'm going to do part B. I don't need you to find the equation of a line. All I want you to do is to evaluate the following for me. Find f prime of, I don't know, let's say 2 if my function f of x is equal to x squared. I don't need the equation of the line. I just need to know the derivative f prime at 2, the slope of the line. Don't care about the actual equation right now. There's a limit involved. I will give you a moment. I would use that x minus c idea. Sweet. I'm going to give you guys a head start. I'll be walking around so that if and when you have questions, I'm available. And you guys do it to it. Looking at this, here it is. If you are struggling, that's okay. We're going to get a lot of practice. I hate that too. I didn't write this initially because I said we're going to find it, and I just started doing the limit, but this is the same thing. Just a little bit more clear. What is f of x? I'm sorry. So f of x is just x squared, right? Minus, what's f of 2? 4, all over x minus 2. This is what I'm hoping to see. Now, if I try direct sub, it fails. But there's good news on the horizon. This is easy to fix. This is the same thing as the limit as x approaches 2. how can I simplify the numerator and denominator? I'll factor it. X minus 2 times x plus 2 is the numerator. And if you don't need all this work, that's okay. I'm just showing everything. Over x minus 2. Now, I don't put the parentheses, but they're really there. That's my grouping. Anything fall out? Okay. So what do we get when I do the limit now? I get a 4. Okay. Check it out. There's a pattern that I want. Like, we don't have them yet. I'm not teaching the shortcut yet. But if anybody who did 3, watch. I'm going to do this. And do you think I can do limits really well in my head? Let's say no. Okay, so this one I think I could, but I'll tell you I'm not doing the limit, but I am using a trick. If you did f prime of 3, guarantee you got 6. If you did f prime of any more, for example, f prime of 4, I think you're going to get 8. F prime of 5, you're going to get 10. How am I doing this? Huh. It's like I'm just multiplying by 2? Weird. Cool. All right. Super challenging. Like, it's weird and the idea is there, but essentially you could go home today and if you want to sound fancy, if your parents ask you what you did, you could say, oh yeah, we found the derivative of a function at a specified point. If you wanted to tell your 8th or 9th grade friend, cousin, sibling, whoever, what you did in class, you could also say, found slope. That's all we're doing. We're finding slope, we're just doing it fancy. Okay, cool. We have one more little comment. Fancy slope, that's a big deal. Now there's even a better word for this. A rate of change is a slope. The big difference in my mind is if I talk about a rate of change, normally I would associate units with it. So if I have a slope, I could say the slope is 5, or the rate of change is 5 miles per minute, or whatever the case is. I would just add the unit. Here's the cool part. When we're talking about slope, it is natural that we will be talking about rates of change. Now, whether we think of them with units or not depends on the problem. If you have a word problem that has units in it and you don't put units in your answers, I will destroy you, just so you know. Like, it's going to happen. I personally won't destroy your grade completely, but the AP test, they will. Okay, units matter. Clarity matters. We'll never say it has. Nope, f of x has a slope or whatever. Like, real specific all the time. It's super annoying, but I get it. Okay, as we're looking at this, rates of change, we have 2 ways that we can talk about it. Earlier in this year, I believe, and I might be confused because I teach a bunch of different classes, we have an average rate of change. And I hate this. Do you guys recall, did we talk about average rate of change this year? Okay, anybody recall the shorthand? AROC, A-R-O-C. If you want to find the average rate of change, it's super easy. I'm not going to write AROC again, but it would simply be f of x minus f of c. So I'm just picking 2 values, right? Over x minus c. This is the average rate of change. Do you guys want to hear a super weird idea that never occurred to me, and it wouldn't have ever, but I saw it online the other day? How many of you wake up and go to bed in the same spot? Like, when you wake up in the morning and when you fall asleep at night, you're pretty much in the same spot, right? Assuming you sleep and wake up in your bed. Like, everybody agree with that? Okay, velocity has a direction with it, but speed doesn't. So check this out. Do you guys sit still all day long? I don't think so. You guys move all day long. But what's your average velocity pretty much every day? Your average velocity for every day, as long as you sleep where you woke, is always 0. On average, you're moving 0 all the time, as long as you go to bed and wake up in the same spot. Pretty wild. Anyway, that's our average. Calculus doesn't really care about the average, just so you know. I don't care about what is the slope or the rate of change between here and here. I care about what is the rate of change at a single point, at a single instant in time. Okay, I like that language the most. Derivatives care about the slope at an instant in time. What do derivatives care about the slope of? An instant in time. So check it out. We have this interpretation of a rate of change over the course of a day, over the course of some amount of time, but we also, we'll only write this word once because it's so ugly, get what is known as an instantaneous rate of change. Suggestions or assumptions on what I'm about to shorthand this as? I rock. And I use IROC. All right, instantaneous rate of change. All that we have to do is just change it from being over some big period of time to at one very specific C value, like a tangent line instead, which is essentially just doing this, but letting what happen? There's a limit involved. I'm going to write everything out. I want you guys to tell me what this limit must be. I'm taking the limit of the, whoa, what? I'm taking the limit of the average rate of change, but I'm going to do it as x goes to what? C. They are super similar. This is the slope of the secant, and optional, secant, tangent. Only difference. Okay. Now, what this means is that when we ask questions, I can now, instead of saying, find me the slope of the tangent line, I could just ask you to find instead the instantaneous rate of change at some given value. The problems don't change. The wording to set it up does. So, ooh, I love this idea. How hardcore do we want to go? Fantastic. We're going to do an example. And I think this is our last problem that we're going to do today. Ooh, love it. Find instantaneous rate of change. Cool, 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 cool. All right. On A, I want us to do f of x is equal to the square root of x. But I want us to find how quickly does the slope change, or the rate of change for this function, at, we'll say c equals 4. If I'm asking you for the instantaneous rate of change of this function at c equals 4, is there a more concise way that I can write this? The instantaneous rate of change is the slope of the tangent line, right? And how do we refer to the slope of the tangent line a couple minutes ago? F prime of 4. I want you guys to find me f prime of 4.